So my name is Jiangjie, or you can call me Beckett. Today I'm going to talk a little bit about the efforts we have been making on building a Flink AI ecosystem. So first, a little bit about myself. So I'm currently working at Alibaba as a staff software engineer, and before that, I used to work in IBM on mainframe, and then I get my master's degree from Carnegie Mellon and joined LinkedIn in 2014. And then I started working on Apache Kafka and returned back to China last year, started to work on Apache Flink. So right now I'm a staff software engineer and a senior manager at Alibaba, and I'm also an Apache Kafka PMC member and Apache Flink committer. Okay, so I have a lot of slides today to talk about AI ecosystem. It's a big topic, so I'm just going to try to talk as concise as possible, but still give you a picture of what we're trying to do. So first, so this is today's agenda. First, I want to talk a little bit about why we're building an AI ecosystem on Flink. There are already a shit ton of AI framework out there based on different processing engines and systems. Why we're building a new one? So what's the motivation there? And after that, I'm going to introduce some of the efforts we have been making towards our AI ecosystem goal. So first, let's take a look at why we're doing this AI ecosystem around Flink. So before we jump into the motivation, let's first take a look at the very popular architecture called Lambda architecture. So this is actually derived from like the big data world. So when big data first came out, everybody was doing batch processing. No one is doing stream processing. And later on, people realized that the value of the data or insights is closely related to the timeliness of the data. So people want to get the insights more timely. So what they do is that they introduced stream processing. And then the Lambda architecture came out. So the idea is basically you have a batch layer doing the batch processing periodically. And because it's a batch processing, so apparently the insights will have some latency. And in order to offset that latency, people introduce another layer, which is called a speed layer, doing stream processing. But the stream processing it's doing is basically starting from the last batch processing and until the current time. So, and when a query comes, the serving layer is responsible for combining the result from batch processing or batch layer and the speed layer together and serve the query result in real time. So in that case, people get a real-time result, which is a combination from the batch layer and the speed layer. So that's what people do in the big data world, and it's very popular. Almost everybody is doing that. And there's a problem of this architecture. The problem is that although the batch layer and the speed layer, they are serving the same query, but usually they're using different engines. For example, in batch processing world, a lot of people are using like Spark or MapReduce. And for stream processing, usually it's like Flink or Storm. But the thing is that they're saving the exact same query, so supposedly the logic should be exactly the same. However, because they're using different engines for batch and stream processing, so it ends up with two code bases, and it's very difficult to make sure that the processing logic are consistent in batch processing and stream processing. So in order to solve that problem, people started to seek towards this batch stream unification thing. The idea is basically, can we just use one single engine to process in batch and stream world? And the answer is yes. So right now, I think, in general, people think both Spark and Flink can do that. And Spark is trying to move from the batch world to the stream world, while Flink is actually doing the other way around. But in general, I would say those two engines are successful in order to make like batch and stream processing unification in general. So with that background, let's take a look at the machine learning. So what are people doing in machine learning? And you will find that a lot of people, or the typical way people doing machine learning is the following way. So they will do some offline training, which in most cases, it's a batch processing. And after that, they will generate a static model and push that static model to online for inference. And when it's online inference, it's actually kind of stream processing. So there are two problems here. One thing is that there are still two different logic in like the pre-processing for the offline training and pre-processing for the online inference. So they're still using two different engines. And the second thing is that, as we mentioned before, people want real-time insights. And in our case, the model is actually static. So when you train a model, you push it online, it's not going to evolve over time, right? So you have to wait for the next batch processing in order to make the model updated. So let's first take a look at the static model issue and see how people are trying to solve it. So then we came to the solution of online learning or online training. The idea is that when people get the events or the requests from online, after the pre-processing, those events are not only sent to the online for inference, they're also sending back to the message queue for like online training. So the online training part will actually take those online events back and continuously update the model and push the dynamic model to inference. So this is what we call online training. And apparently it has a bunch of new requirements coming out. So one thing is that we need more prompt model update, obviously. And also a dynamic model need to be continuously trained. And people have to do progressive validation as well. And because the model are keeping generated and are pushed online, so you have to have more sophisticated monitoring and model deployment or rollback when the model doesn't work well. So and it kind of reminds us about the big data world, right? So when people want to initially start with like batch thing and people add the real-time thing to it and start to do the Lambda architecture. So we can actually do exactly the same thing or similar thing in machine learning. So what happens is that people end up doing something like this. So the upper part in this diagram is the like online part or real-time part. So it generates a dynamic model. And the offline, like the lower part is the offline part or traditional like static model part. So it's generated a static model. And both of them is going to push to the online inference to do the prediction. And as you can see, it still has a problem there. So the problem is that the pre-processing part are still usually handled by two different engines, because this one, it's a batch processing, so people are used to it to use like a Spark to do this part. And for the online part, people usually like to use like Flink to do it. So in order to solve this problem, we need to look into what is the solution there. So when we look at the online path, we found that for the pre-processing and inference part, it's actually pretty like latency sensitive, because it's either online or nearline processing. And Flink is a good option for that. It's kind of difficult for us to find a replacement of that. So then the idea become obvious. So can we just simply use Flink everywhere? And if we can use Flink everywhere, then we solve the problem. We only have one code base for online and offline, for batch and stream. And we don't have to deal with many different systems. You only deal with Flink all the time. It sounds like a fantastic idea. Let's see how can we do it. By the way, there's also some additional values. As you can imagine, Flink does not only support machine learning. Flink has also very rich like a processing ecosystem, right? So you can use SQL to process, you can use table API to process, you can use data stream to process, and you can even use CEP to process. So once we put the machine learning story there, as you can imagine, what people can do is that I have some online events coming in, and I can use SQL or data stream to process it. And then I can feed those like processed data into my machine learning pipeline to train a model. And once the model come out, I can put it into a CEP to do my like a fraud detection or something like that. So it becomes like an entire like one-stop data processing and AI solution. So that sounds very attractive. So that's basically our motivation or our vision on how to build a AI ecosystem around Flink and why we're doing that. So in order to do that, we need to look into like all the like small building blocks we have there in Flink. And this is basically the Lambda architecture for machine learning we mentioned before. And if I added the model validation part, so basically when you have a model there, before you want to push it online, you want to validate it. So if we look at this and we divide this picture or diagram into a few columns or machine learning stages, we can look into each stage and see what's there, what is the requirements of that, and what are our efforts in Flink like community or ecosystem that is there trying to solve those requirements in each ML stages. So for the first stage, we call it data acquisition. Essentially, you need to have data. You have a lot of different data sources, and you want to ingest your data into the Flink AI ecosystem so it can be trained and can be inferenced. So apparently, Flink has a very rich connector support already. And one thing missing, or it's not provided for from open source Flink, is the dataset management. So I just put it in the red font here. And the second stage, in Flink, we have stream batch unification processing, which is good. And we also have very strong SQL support. That's a pretty unique value from Flink. So it looks like from pre-processing stage, everything is good. We're happy about it. And for the model training part, there are a few ongoing efforts, and we're going to talk about them in this presentation. So namely, there are enhanced iteration, Flink ML Lib, and deep learning on Flink. So basically integrating TensorFlow and PyTorch into Flink. And then the next stage would be model validation and serving. So in this part, we need dynamic model serving, we need model management, and we need to have a way to roll out or roll back our models. And those primitives or building blocks are not there in open source Flink. And lastly, for the inference part, as we mentioned before, because the models are pushed online more frequently, we need a way to do online monitoring and online evaluation. And so those parts are also not part of the open source Flink at this point. So, and finally, we have already got a Flink ML Pipeline and Python support, some of the Flink ML Pipeline and Python support in open source Flink. It is important across all the stages, starting from pre-processing to inference. So, and today, this presentation, we're going to cover the following parts, which is in yellow. Okay, now first let's take a look at the Flink ML Pipeline and Flink ML Libs. I hope the first section I have explained clearly on why we're doing AI on Flink and what is the big picture and which part we're working on. And now I'm going to just talk about a few efforts that was in that large picture and basically talk about them in details. So one thing is Flink ML Pipeline and Flink ML Lib. So Flink ML Pipeline, the API has already been checked into Flink in 1.9. And we're doing something checking in the Flink ML Libs right now. So what is Flink ML Pipeline? So the idea behind Flink ML Pipeline is that when we look at machine learning, we're actually serving two types of users. One kind of user is that they are like algorithm developers. They write machine learning algorithm and models. And the other type of user, they are actually like the machine learning users or end users. They do not develop their own model or type. They simply stitch things together to form an entire ML logic to use it. So, and ML Pipeline is essentially trying to satisfy the needs from both ends. And the idea of ML Pipeline is that it's originally from a paper called scikit-learn. And the idea is that they believe that in machine learning, there are only two kinds of data processing. So one type of data processing is transformer, which is mentioned here. And the idea of transformer is saying that I'm just going to transform some data into another set of data. So it's data-to-data transition. In our example, it's going to be pre-processing or inference. So the input is data and output is also data. And the other type of data processing would be estimator. So what does the estimator do? The estimator basically do the data to model transition. So the input of the estimator would be data, and the output of the estimator would be a model. So in our case, more specifically, it's actually the model training part. So this is basically the idea behind the machine learning pipeline. And now let's take a look at the first kind of users who are ML Lib developers. So right now we have, so Alibaba has this internal library built based on Flink, and it's been in production for quite a while. We're actually picking all those algorithms and we're trying to check them into open source Flink one by one. So there is ongoing efforts to basically implement a bunch of estimators so we can let a user to use them out of the box in open source Flink. So the new library would be ML pipeline based, and it's going to be table API based, and they are battle tested algorithms. So we listed some of them here. So our goal is that in 110 we can hopefully check in at least 7 most popular traditional machine learning algorithms in Flink ML Libs. For the machine learning pipeline, once we have those like estimators or models checked in, how can user use that? So this is a simple example. So what a user can do is that, let's say user have some input as a table or as a training samples. So they build a pipeline which only contains one single estimator. And then they will call estimator.fit on those like input table or the training samples. And like we mentioned, the estimator is doing the data to model transition. So what it does is that it's going to generate a model back out here. And this is like the training process. And after that, the same pipeline can be used, and it's going to use this model to the inference. So model is actually a subclass of transformer. So what a user can do is that they can put some testing data here, and they can call model.transform, and they put the input table or the testing data to this transformer pipeline, and they get the predictions out. So this is a simple case. And a slightly more complicated case would be, people do not only have one estimator in their pipeline, they can have a transformer and followed by an estimator. Similar as the previous example, people will have like input samples here, and they will call ML pipeline.fit with this input. And as a result, you will have a result pipeline, which is a model pipeline. The difference is that the estimator in this pipeline, in the original pipeline, would become a model because it's trained using the input training sample table. And same thing, we can put this pipeline here for inference. So what people do would call pipeline.transform, and they feed in the testing data or the data that, or the samples that need to be predicted, and the result coming out would be the predictions. So this is the basic idea of machine learning pipeline. So what's the value of machine learning pipeline? It basically has two values. One thing is that it unifies the API of model training and inference for the end users. So the end users do not need to worry about or care about what exactly model or algorithm they're using, because all the APIs are simplified to just two classes. One is transformer, the other one is estimator. So, and the second benefit is that it ensures the consistent logic between training and inference, because when you form a pipeline and you call pipeline.fit, the exact same pipeline will be used for inference. So in that case, you do not need to worry about saying that, okay, my offline training pipeline may be different from my online inference pipeline. They're actually exactly the same pipeline. Okay, so that's about machine learning pipeline. And another effort we're making is to integrate deep learning into Flink. So what exactly does that mean? So this is like a flow for, we already mentioned before, so you have data acquisition, then you have pre-processing, training, validation, then model serving. And in this case, as you can see, normally, or like the mainstream companies, what they're doing is that they may be using Flink to do the data pre-processing. However, for the model training, test, and validation, and model serving part, if it's deep learning, usually they're using something like TensorFlow or PyTorch. So, so the pipeline is essentially, this entire machine learning, deep learning pipeline actually consists of 2 different systems. And it's actually more than that. If we zoom in a little bit, what people usually do is that they will have data acquisition and data pre-processing in Flink, so it's a Flink job in a Flink cluster. And in order to communicate, or in order to put all the results emitted by Flink to TensorFlow, they might need to introduce some intermediate storage here. Maybe it's a queue or some HDFS here. And then they have to run the TF job in the model training part in another TF, a distributed TF framework in a cluster or environment. So it's actually at least 3 systems involved in this entire process. So it's hard to operate and it's easy to make mistake because you have to deal with a lot of different systems. And the idea we have is basically we're trying to integrate TensorFlow into Flink. As we mentioned before, we try to do everything using Flink. So in that case, people only deal with one system. So how exactly we're going to do that? Here's how. So, in this slide, the upper part is actually the part that we just showed you. You have 3 systems involved in this process. And the lower part is what our solution is. So essentially what we're doing is that we're trying to launch a TensorFlow, distributed TensorFlow framework in Flink, inside Flink. So each of the worker, as you can imagine, becomes something running alongside or with the Flink task manager. So when user write a TensorFlow model, when they put it to Flink, we are able to run their model distributedly, leveraging the Flink task manager. So what we do is that each worker, as you can imagine, it becomes a Flink operator. So the number of workers becomes the parallelism of that operator. And the PS also becomes a Flink operator. And the number of parallelism also becomes a Flink, the number of PS node in TensorFlow. So by doing that, as you can see, we can actually basically have one single Flink job in the cluster or environment, and we can save the queue in the middle also. So people just need to run single Flink job, and it becomes, starting from pre-processing to the model training, and eventually you get a model out. So it dramatically simplifies the system. And so what's its relation with the ML pipeline? As you can see here, okay, it might be a little faint here, but so essentially the UDTF here, you can think of it as a transformer, which is doing the data pre-processing. And the rest part, you can think of it as an estimator, right? So the estimator, as we mentioned before, it's mapping the data to model. So that's exactly what this deep learning training part is doing. So an estimator can actually, the implementation of an estimator can actually be a deep learning training part. So that means our machine learning pipeline abstraction or API works fine for both traditional machine learning and the deep learning. Okay, cool. With that, let's take a look at the enhanced iteration and dynamic model serving. So first, let's take a look at the enhanced iteration in Flink. So Flink, it's something very unique in Flink, which is that Flink has this native iteration implementation. What does that mean? So Flink basically has this feedback edge concept. So you only describe your iteration. You do not actually run write a for loop. As for people who are using Spark, they may know that if you are trying to implement an iteration in Spark, what you do is that you write your own for loop. But in Flink, it's different. You just describe your iteration, And the framework will just add a feedback edge, so it's going to be run natively in the Flink job. There are some caveats right now in Flink dataset or data stream iteration API. One thing is that right now it's not the multi-variable iteration is not supported, and also the nested iteration is not supported. We're trying to solve those two problems. Meanwhile, we're trying to add yet a new way to define like mini-batch iteration, so we can actually have a more strong semantic when we do iteration in the data stream. So what exactly does those mean? So let's first take a look at the multi-variable iteration. So, in each iteration, there are 3 building blocks or 3 basic elements. One thing is iteration variables. That means those variables are going to change as the iteration goes. And the second part is step function, which means it's going to be executed for every run of iteration. And finally, you have termination condition telling you when you want to stop the iteration. So in our case, the multi-variable iteration basically means that we want to modify multiple variables when we're doing iteration. It's not supported in Flink dataset or data stream right now, but we're trying to add it. And the second part is nested iteration, which means like you have a for loop inside the for loop. Here, so it's pretty straightforward. We have an iterate here, and inside this iteration block, we have another iterate here. We're also trying to support this kind of pattern. And finally, we are adding like the mini batch iteration here. So the mini batch iteration is the idea of a mini batch iteration is trying to solve the semantic of iteration on top of data stream. So as you can imagine, when we're talking about iteration, we'll usually say, okay, how many rounds I want to run for an iteration, right? So however, if it's a data stream, it's like an unbounded stream. There's no way for you to define the number of rounds you can run. So what currently Flink is doing is that we're trying to just put let every event loop over and over again until they're not emitted anymore, right? They're not emitted to the feedback edge anymore. So with the mini batch iteration, we can actually define the number of iterations on top of data stream. So the idea is basically we're going to chunk the data stream into multiple mini batches, and each mini batch iterates independently in the iteration loop. And the results are emitted in the mini batch order. So as an example here, let's say we have a data stream and we chunk it into mini batch 1, 2, and 3. And mini batch 1 has already gone through the loop and been emitted. And mini batch 2 is still in loop, being iterating on. Mini batch 3 is not, has not entered the loop yet. So with this mini batch iteration, we can actually have a more native support for stochastic gradient descendant or SGD. So this will help the machine learning algorithm to converge faster. Also we will have native support for online learning. So what exactly does that mean? So this is I hope you still remember that we mentioned that in the big AI ecosystem picture, one problem we are trying to solve is dynamic model serving or dynamic model update. So the idea is that we want to dynamically update the model we're using for online inference without restarting our job. So how can we do that? So, and iteration happens to be the answer. How? So if we take a look at the iteration in machine learning when we do the training, what happens is that we will have like an initial model here, and we feed model into the iteration loop here. And the gradient computing is essentially taking that model and sample to use that model to do prediction and see how far away it is from the actual label that we labeled there. So it generates a gradient. And when we reduce the gradient, we get essentially the delta of the model that needs to be updated. So it loops back to the model node here, update the model, and push the model version 2 here to the gradient computing again. And then the gradient computing will basically use the sample and updated model to do the prediction again and to see how far away this version of the model is from the actual label. and generates the model, like the delta of the model, and then loop it back again. So this is essentially how the iterate and converge loop in machine learning training process. And if we take a closer look at it, inside this like the red block or red box, we have this model here, and it's actually updating the model to the gradient computing node here. And the gradient computing node takes a sample and do the prediction, then compute the gradient. So it looks like we already have, sort of have the dynamic model updating without stopping the job. So if we put it into the big picture here, as you can see, we can have like a perfect fit in the dynamic model serving. So for the online or offline part, when they generate a model, they just put the dynamic model or static model into the model validation part, and then they feed the model into online inference. So, and this model could be version 1, 2, and 3 all the time. And for the online part, we will have continuously coming in events, and we're going to generate samples, feed into the inference path, and then do the online inference. So this dynamic model updating part is already done if we use the same mechanism as we do in the iteration. Okay, and finally, let's take a look at the Python support. So as we know that in machine learning world, Python is like the native language. So data scientists only write Python, they do not write Java. We learned this in the hard way, but that's the truth. Okay, so here's our efforts. So right now in Flink 1.10, we already have the left part. In Flink 1.9, we already have the left part. So we have Python table API support, which means that you can use Python to write table processing programs in Flink. And the way it works is that we're essentially translating the Python language to Java language and build the DAG in a Java way. So it's like the API-wise, it's one-on-one mapping from Python to the Java world. And we're using RPC and maybe Py4j for this. And in Flink 1.10, we're trying to also have the Python UDF support as well. So Python UDF support is going to be more difficult than the Python table API part, mainly because it's on the critical section. So, and what we have to do is that we have to essentially, besides every task manager running in Java process, we have to also start a Python process running aside with the Java process and run the UDF here. And so all the events that flowing through this Java process or task manager need to actually be sent to the Python process to do the process and send back to the Java process. Then we can send the result out to the next operator in the Flink DAG. So this will have some performance overhead here. And I think the key thing here is that we're going to try to reduce the performance overhead as much as possible. And right now we're working with Apache Beam community on doing that. I think it's critical for the adoption of Flink in AI system. So yeah, it's very important. And besides that, we're going to add a few more Python API support. Namely, they're going to be Flink machine learning pipeline and Flink AI extended. So Flink AI extended is the name of the project that hosts the deep learning on Flink part. You remember the TensorFlow running on Flink part? So that's essentially an ecosystem project, and we put all the code in the Flink AI extended. It's also open sourced. And also we're going to put the Python API support for data stream as well. All right, as a summary, so I think we believe that Flink has unique values in AI use case. So there is a part that is Flink is difficult to be replaced, and if we have to use Flink in our AI ecosystem, the idea becomes: can we just use Flink everywhere? And it seems to be attractive and seems to be doable. And then we come up with this like Lambda ML architecture with Flink used everywhere. And we are, in order to achieve that, we're doing a lot of things. And we talked about like a Flink ML Pipeline, Flink ML Libs, deep learning on Flink, iteration enhancement, Python API, and such. Okay. All right, so that's pretty much what I want to say today about Flink AI ecosystem. Okay, thanks. And very important thing, we're actually hiring. So if you want to work on all the AI ecosystem part, please send me an email. And also, we're going to have a Flink Forward Asia in Beijing it actually should be November, not December. Okay, I forgot to update that. So yeah, so remember to register. All right, thank you very much.
I think we have 2 minutes for a single question, and then just grab back it after the talk. He will be around and happy to answer all the other questions.
Yeah.
Thanks a lot. Really cool project. I'm just curious about your iterations. So they look extremely familiar with the iteration project we presented last year at Flink Forward. Mm-hmm. Probably you're familiar with the multi-step nested iterations for Windows and our solution. Is it the same project, or did you create something from scratch?
You mean the iteration part, right?
Yeah.
The iteration part, it's pretty much the same project. But I think there are two parts of it. So the one part is that we're trying to solve the nested iteration and multivariable iteration part. So that's like from the original project. We haven't changed anything.
Does it use like augmented watermarks?
Yes, exactly.
Yes.
So
it's exactly the same project.
Yeah, that's the exact same project. And we're adding one more part to it, which is use a mini batch iteration.
Do you use our source code, or did you develop it in-house at Alibaba?
Sorry, what's that?
Did you use our source code, our project, or did you create something?
We use it. We actually developed by ourselves.
I see.
Yeah,
cool.
Yeah.
Thank you very much.
Okay, thanks.